Oh, okay. So someone asked about 6.4 number 3. So just to remind you which one that is. I'm not going to be super helpful on this because it already has a hint. So and actually, if I say too much more, it kind of gives it away. But basically, here maybe I'll. It's a little small if I lay it down. Is that gonna focus? Here, hold on. There we go. So suppose that you have a continuous function f from ab to r, and its integral on that interval is 0. Prove that there is some point in that interval at which f is equal to 0. And you're given a hint. Use the extreme value theorem and the intermediate value theorem. Okay, so like I said, the hint is doing most of the legwork here. Just recall, you have a continuous function on closed interval AB. What's the extreme value theorem tell you about a continuous function on closed interval? Well, you know that it has both a max and a min. What's the intermediate value theorem tell you? Well, it tells you that for a continuous function, basically, if if I'm paraphrasing here, if you know a particular range of values, right, for your continuous function, it has to attain all of those in between, say, two extremes. If you like, it has to attain all those, right? There can be no gaps, right? So if you remember, IVT was in chapter 3. Uh, so I think was it in 3? Yeah, it was in 3.3. Right, so there's statement, intermediate value theorem. So these two things combined tell you that there's got to be at least one. There's got to be at least one point at which this thing is 0. So why do they say that? Well, like I said, I don't want to totally give it away, but think about these things. So think about the hint. You have a function f that both of these apply to on that closed interval. Okay. Use what you know about integrals. You can look at this, any of the through 6.1 through 6.4, but 6.4 alone is going to tell you what you need here, and you should use what you know about integrals to say if this thing has an integral and it's 0, why does it have to be equal to 0 at one of these at some point here? Again, just think about these two things mentioned in the hint together with what it means if you can write out what this thing is. So using Archimedes Riemann, you can think about this as either of the limits of the Darboux sums. For instance, that's one thing. That's one way you could think about it. There's easier ways you can think about what this tells you, but it will pop directly out of that. Okay. Let's see here. Oh, number 3 on the final. Let me see here. Oh. Yeah. So, did we do so back when we first did sequences, I believe in your lecture notes there you should have one example of this that was very similar. In fact, it might even be. I think I did it directly from the textbook. I could be wrong. Maybe I did a slightly different one, but let's see. I'm pretty sure I did one of those. Yeah. Like I said, I'm pretty sure we did an example that was very similar way back then. It's hard to remember, but I I want to say that is the case. I remember doing at least one example of a sequence defined in a very similar way, although I don't see it in the. Yeah, okay. So, I know that we at least did an example of this recursively defined sequence. I know that I at least did that. I can't remember if I did any other examples, but the one that involves the Goldman ratio, we did this one. So basically, this dealing with recursively defined sequences, if you've already figured out how to do three, then that's good. But dealing with recursively defined sequences, this is a nice example. So this is page 44 in the book. This is like a very simple example. There may be some, I can't remember where I grabbed that particular example. I think I just came up with that one. But anyway, yeah, recursively defined sequences are fun. So this little observation can help understanding as well. Anyway, so but I won't say too much more about that. Yeah. That's good. Um, number five. Yeah, number five on the final. Oh, that's it's not too bad, right? It's not too bad. This is actually a textbook problem. So it's actually, I believe that's a problem in the textbook. It's not one I assigned, but it's a problem in the textbook. So yeah, looking at the looking at the final again. As I said, I spy. So I spy a couple of parts, of course, that one F that's from chapter 8. Um, and I spy one other problem from chapter 8 material, which I'd already hinted. If you haven't watched the chapter 8 lecture, then you should definitely have a look at that, because I talk about some trickery on showing some certain inequalities using chapter 8 stuff. There's actually a similar problem in the homework, in the chapter 8 homework. I think it's 8.2. But anyway, like I said, ask. You can ask away if you know, if you. I will try to be. I'll try to be more helpful with the homework problems, unless I feel like me saying one thing basically does it for you. Sometimes I do it anyway. I know in the last problem session, some of those that I wrote out, I pretty much wrote out the whole thing. But so sometimes that will happen accidentally, but I will try to not totally give it away. There are some that I can actually say something without totally giving it away, but the others, if I'm reluctant to say something, it means that there's not a whole lot you have to say to get from your assumptions to what you're trying to prove. But anyway, so ask away. I will be here for another, at least like another, what is, it's almost 2. Yeah, I'll be here for like at least another hour ish.
Get my grip.
Okay. So 4.3 number 20. 4.3 number 20 is one. So we talked about this in the last problem session. So look at this thing. So defines this function x minus x squared if x is rational, x plus x squared if x is irrational. Show that its derivative of 0 is 1. That's not too bad. And yet there's no neighborhood I of the point 0 in which the function is monotonically increasing. So what this is supposed to be showing you is basically a warning to drawing too much from number 19. So 19, the one before it says, suppose you have a differentiable function. Its derivative is continuous at 0. Its derivative is at 0 is positive. You have to prove that there's an open interval containing 0 for which this thing is strictly monotonic. So this thing fails it. Okay, even though its derivative at 0 is positive. So what goes wrong? How can number 20 and number 19 simultaneously be doable? And well, you should know what exactly is wrong here. There is definitely a missing assumption. There's something that f in number 20 does not satisfy that f satisfies in number 19 that makes a big difference. So that's one thing. And the other thing, which I said last time, is so together with that, right? So question is f continuous? Is f prime continuous, right? These are even at 0. So the question is, these are two assumptions. So f is differentiable here, and f prime is continuous at 0. So the question is f prime continuous at 0? You know what the answer to these questions have to be, because by 19 this statement would be false. So you know what the answer to those questions have to be. The other thing is use the density of the rationals and irrationals in the reals. Okay, so those two things together guarantee you that you don't have any interval, or you don't have any interval I of that contains 0. So you have no neighborhood of 0 on which this thing is monotonically increasing. Why? Because the density of the rationals and irrationals means that you have sign flipping everywhere. Okay, so you have sign flipping everywhere. This is sign flipping of the derivative, that is. So this means that this thing it can't be monotonically increasing, which would require its derivative to be positive, right? This is the chapter, or the section of the chapter where you first show rigorously, your basic criterion for a thing being increasing. So I might remind you, there's this corollary here, page 105. So criterion for strict monotonicity, it's exactly what you think it is. If you have an open interval and a function is differentiable on the open interval, if its derivative is positive for all x and I, then it's strictly increasing, right? So you already know that, and you know that I can replace this by swapping to the negative. I can make a similar statement about strictly decreasing functions. So that's what I'll say. But since you asked two questions and I didn't, here I maybe said more than the other one. I'll throw you more of a bone on the last question. So the other question you asked about was 6.4. So let me 6.4 number 3, I think, which was this question. You have continuous function on closed interval AB. Its integral is 0, and so you're supposed to show that there's some point in this interval at which the function is equal to 0. And the hint was to use extreme value theorem or intermediate value theorem. So here are some basic questions you can ask yourself. So one, am I done if I know that my function takes values that are both negative and positive? Well, yes, right? So if I knew that this function f, was negative anywhere in this interval, I'm immediately done by the intermediate value theorem, right? So if there is a single point here in this interval AB where f is negative, because f is continuous, since it's negative somewhere in this interval, unless it is negative everywhere, I should say, right? If it is both negative and positive in this interval, then, well, what has to be true? It would it would have to cross 0, right? It would have to touch 0 by the intermediate value theorem. So maybe I should rephrase that because it came off a little bit confusing. So basically, can this function take values that are both negative and positive and not touch 0? The answer is no, right? So if there are values in this interval, so if there's points in AB at which f is positive and another point at which it's negative, by the intermediate value theorem, since it's continuous, it would have to touch, right? So then what's the only way you could get around that issue, right? And you might say, wait, why is that an issue? That's what you're trying to show. I'm thinking in terms of contradiction, right? So I'm trying to make this fail as hard as I can. So what would have to occur for this to not be the case? Well, if f took both positive and negative values, that's no good by the intermediate value theorem. Okay. So by intermediate value theorem, that's no good. I would have guaranteed by intermediate value theorem that f of some x naught is equal to 0. Okay, and that's because f is continuous. So then what are my alternatives to that? Well, I could have a function f that takes nothing but negative values, or I could have a function f that takes nothing but positive values, right? And you might say, wait, why aren't you including... So let me write out. So suppose not, i.e., suppose there is no x naught such that f of x naught is equal to 0. Okay. This is kind of an awkward contradiction. I really don't need to do this by contradiction because essentially what I'm going to be doing is saying suppose not, and then at every step I'm going to be contradicting myself. So you don't have to do this as contradiction, of course. If you know that if you have a direct proof, then a proof by contradiction is trivial. You just suppose not, and then you copy paste your direct proof there, and you've shown the opposite of what you suppose. So you're done. So it doesn't matter. This is a little bit inelegant here. So suppose there's no x naught such that f of x naught is equal to 0. Then f cannot take both positive and negative values on AB, since if it did, then by IVT there exists an x naught such that f of x naught is equal to 0, right? Because f's continuous. Okay. So f can't take both positive and negative values and still get away with not having this x naught, right? Okay. So then there's only two options here. One, f is strictly positive on AB, and two, f is strictly negative on AB. And you might look at these two cases and say, wait, they're not really exhaustive. Okay? They're not really exhaustive because what if f of f is greater than or equal to 0? What if f is less than or equal to 0? What if f is identically equal to 0? Well, we're done in each of these cases. We're done because if f is less than or equal to 0, and it actually is inclusive, meaning that there is some point that f is equal to 0, well then we have such an x naught, right? So in each of these cases we're done. Again, you see why I said it's really awkward actually to do this this is not really contradiction, although I'm phrasing it like that, so it makes the wording a little awkward, but you could just delete this, you could just cross out this first line, and argue in the exact same way, saying, well, if f takes both positive and negative values, I'm done. If there exists such an x, I'm done. So if I have these inequalities, or if f is identically equal to 0, then clearly I'm done. So the only remaining cases where it is possibly up in the air what's going on, right? So if f takes both positive and negative values, I'm done. There is such an x naught. If there is such an x naught, but other than that it's positive or negative, then I'm done. And if f is identically equal to 0, clearly I'm done. So the only thing that is left here is f is always positive, f's always negative. But f is continuous, right? So by the extreme value theorem, in each case, right, there exists some min in the case of 1 and max in the case of 2, such that, and we'll call the min little m and we'll call the max big M. So in the case of 1, I get that f of x is greater than or equal to little m, which is strictly positive since it is attained, right? Little m has to be strictly positive since f is strictly positive, and f attains this little m somewhere, right? At least at one point by the extreme value theorem, right? So there does exist some x naught prime such that f of x naught prime is equal to little m. Okay. Similarly, there is a big M that's a max in the case of number 2, so that f of x is less than or equal to big M, which is strictly negative. Okay, the same thing is true. All right. Why does this get you what you want? So you got these inequalities. All right, why does this finish what's going on? So let's write these inequalities here. So why am I done once I have these? Oh, there we go. Well, by monotonicity of the integral, then I have the integral from a to b of f. Just going to write it as f. Here, like that. So the integral from a to b of f in case 1, right? So this is in case 1. This integral is bigger than or equal to the integral from a to b of the constant function little m. Okay. But what is the integral from a to b of the constant function little m? Well, this is m times b minus a, right? And since little m is positive, and since this is an interval, b minus a is positive, this quantity is strictly positive. But I know that this is equal to 0, right? The integral from a to b of f is equal to 0. So I'm saying that 0 is strictly bigger than 0. That's a contradiction. In case 2, what is going on here? Well, in case 2, similarly, I have that the integral from a to b of little f is less than or equal to the integral from a to b of big M. But again, this is just a constant. I know how to compute the integral of a constant. So this is big M times b minus a. By this inequality, since big M is negative and b minus a is positive, this is negative. But I know this quantity is actually 0. So again, I get 0 is less than 0, which is also a contradiction. Right? So these only two cases that didn't immediately terminate, right, actually end in a contradiction. Thus, there must exist some x naught such that f of x naught is equal to 0. Okay. So that's how this sort of thing goes. There's actually uh, depending on the assumptions made, this question of how much do you know about a function if you know that its integral is 0 over some set, it's a question that comes up again and again in math. This isn't the only type of question that can be asked about that. You can play around with the assumptions to see what's going on. So in fact, there's some assumptions that you can make. If your f in question is regular enough, if you know enough about it, then its integral over some some set being 0 could mean that the function itself has to be 0, right? You might think to yourself, what would you basically have to impose on f for that to be true? But anyway, so that's how this goes. So more questions? I'll be here. Like I said, I will be here for at least another 35-ish minutes, 36-ish minutes. So I will put the tunes back on so that you don't hear my labored breathing over my 20th Mountain Dew can today.
go. Yeah! Complete.
You hate.
Yeah, so for 8.2 so here's the problem. So I mentioned this. I actually even wrote it in the chapter 8 lecture. So there's number 1. It's proving that inequality. So like I said, I think I even wrote that inequality down and mentioned that exercise in the chapter 8 lecture. So basically, you're just using the Lagrange remainder theorem, and to see how that works, remember we did this proof of the irrationality of E, and it made use of this inequality, which came directly from the Lagrange remainder theorem. The proof that I skipped but just mentioned of this property, this bound on the Euler-Mascheroni constant, also arrives at some inequality here that actually just pops out of the Lagrange remainder theorem. So those are 2 examples of how to use the Lagrange remainder theorem to come up with some inequality that otherwise you might not be able to. So that's my hint. My hint is, yeah, this just says prove some inequality. So if this just appeared somewhere, you might not know what to do, what the trick is. But since it is in this section, and this section literally is in its entirety the Lagrange remainder theorem plus applications of it. So this is Lagrange remainder theorem. So use Lagrange remainder theorem for the Taylor series for square root of 1 plus x, and that does it.
「こんじきたたえ」 取り巻くこの世界に白い羽が舞い降りた限りあるからこそ強く美しく光る刹那を見つけた無機質に閉ざされたうつろな日々に初めて夢を見た君に触れたいそんな存在に気づかない君はさよならってある日言った幾千の月日を越え目覚めた積もる想いをなぜ伝える術さえなく見送ることしか許されていないのふと見せる表情が大好きだった話してくれた夜幸せだった回るはずのない歯車がきしみ回るほどに落ちていった分かっていた叶わぬ恋だけど止められなかった君がいない永遠ほどこの世界中に怖いものはない
Okay, so I think that's about it. If no one has any other questions. So, good luck with your final exam. If you have any, pressing questions, you really can't figure out something, you can email me. And like I said, I can't guarantee that I'll be, like maximally helpful, but I may be able to give you some hints if you need them. So anyway, yeah, just let me know. I'll be around and on email, so I'll try to get back to you as soon as possible. But yeah, anyway, like I said, let me know if you have questions about stuff, and good luck with your problem sets and your final.